Hi, we're Group 36, and today we'll be presenting the Multi-Purpose Device Controller.
Hi, my name is Kenny Dow, and I'm a 24-year-old computer engineer with hopes of landing a software engineering job. Currently, I'm working as an IT service desk intern at a South Florida-based company.
Hi, I'm Johnny Blanc, and I'm a 29-year-old computer engineering student here at UCF, currently an IT intern, and I have hopes to be a software engineer.
Hi, my name is Jason Jean Lewis. I am a 25-year-old computer engineering student from West Palm Beach, Florida. I am a member of the National Society of Black Engineers and a member of Alpha Phi Alpha Fraternity Incorporated, with hopes of pursuing a career in embedded programming.
Hi, my name is Mohammed Al Fadi. I'm a 24 years old international student from Oman. I am a senior electrical engineer at UCF. I hope to pursue an electrical engineering career in hardware design and to work for major companies that relate to power.
Gamers today juggle a variety of platforms, PCs, consoles, and even mobile devices. But the controllers we often use limit us. They're built for one system, forcing us to juggle a tangled mess of wires and remotes just to play across different devices. There's a need for a better solution, a controller that adapts to our needs, not the other way around. Our innovative design lets us ditch the controller clutter and seamlessly switch from favorite games regardless of our platform. But a great controller needs more than versatility, it needs precision. Ever felt that frustrating drift on your joystick? It ruins your aim and throws off your entire game. That's why we're incorporating Hall effect joysticks. These innovative sensors eliminate drift, ensuring your every move translates perfectly onto screen. This project seeks to develop a highly durable controller with the universal compatibility across multiple gaming platforms. Our core objectives center around eliminating stiff drift through innovative Hall effect joystick technology, ensuring precise and reliable input. Additionally, seamless Bluetooth connectivity empowers wireless freedom, enhancing user mobility and reducing cable clutter. We envision further advancements through software for customizable settings and configurations, along with broadened capabilities for a ever-expanding range of consoles. Finally, we're exploring the implementation of a rubberized exterior to optimize grip and handling comfort for extended gaming sessions. This controller represents a paradigm shift designed to revolutionize the future of gaming control.
Here we will discuss our project test plan. First, we designed a PCB with components that complemented each other. We then confirmed that the components were getting the correct readings. After, we verified connections to multiple devices. And lastly, we implemented techniques to improve accuracy and responsiveness.
When I'm filling out soldering. Reservoir says if I need help with senior design, I can hire a student to senior design. I think that's everything. Let's just make sure we clean up here. Oh. There you go. Oh, you're messing up your table.
Yeah, I know.
Show a video. Oh, okay.
I don't think this is mine, so I'm gonna leave that.
Nina, what type of computer do you have?
A Mac?
I'll forget it.
Why?
I brought this,
Our team used Eagle software to design a schematic for our gaming controller. We have 13 major components on our PCB circuit. The bar components include USB-C and a charging circuit for the battery. The battery takes the voltage from USB-C, which is 5 volts, and regulated to 3.7 volts. The voltage regulator then supplied the required 3.3 volts to our MCU, which interfaces with the rest of our components.
We decided on this component placement for comfortability for the user and current button layout for other on-the-market controllers. Ergonomics are important for extended play sessions and minimizing fatigue. The main interface buttons being the action buttons, direction buttons, and joysticks, along with the placement of our USB-C charging port.
The devices we were able to connect to were Androids and Windows PCs. Connection to any other device would require further licensing. Here are the accuracy techniques we used to improve the responsiveness of our controller. We used a dead zone, which is a small area around the center of the joystick that ignores minor movements, preventing accidental inputs. We also used debouncing, which delays function calls for rapid inputs, preventing accidental actions and improving performance. As you'll see in the next slide, joystick values are noisy and aren't representative of the actual joystick position. In this next slide, you'll see the dead zone is applied and the joystick values are pretty much at 0. When a button is pressed, we introduce a short delay before reading the input. If the input state remains consistent after the delay, we consider the button press as valid. This helps filter out the noise caused by bouncing contacts. Gamepad LA is a free tool that measures the perceived delay between gamepad button presses and the response on screen. It works by measuring the time it takes for the gamepad's analog stick data to change. While it provides valuable insights, factors like game engine processing and display refresh rate also affect overall responsiveness. Here are the results after 10 test runs. Our controller latency averaged out to 2.788 milliseconds. So here's a demo of our controller. The blue LEDs will flash when it's searching for a device. And once we turn on Bluetooth, we pair with our device, and then the LEDs will flash in a rainbow effect.
You don't have enough net open. On our initial design of our printed circuit board, we neglected to include a ground pin for our voltage regulator, which led to multiple components to not function properly and display false readings. The solution we found for this was to route a wire from the ground of one component to the ground of a different component that was included on our voltage regulator circuit.
And also we had a problem with the programming circuit. We have USB-C CB2102 and ESP32 components to program our ESP32, and these components were not properly communicating with each other. So our team decided to change the plan to program the controller. We used a 5-pin header that included the necessary communication pins, which are transmit, receive, 5 volts and 3.3 volts and ground. And then we connected the pins on both our PCB and an interface that has its own programming circuit, and the issue was resolved.